So let's continue hopefully quickly and go to some of the. We are done with section 1, the gamma function in section 1. Hopefully section 2 will be easier than because it's basically taking the derivative of the gamma function and then we define this so-called digamma function and polygamma function. Just basically keep doing derivative, you kept the polygamma function. And the textbook actually start with the Euler infinite limit, but we don't have to. We can use because we already spent the time to divide the infinite product. So we start with that. That is, as in my opinion, is slightly easier. Let's see. Once again, see. That's equation 13.15. So it's the infinite product stuff again 1 to infinity after 1 over n minus c into infinity. Okay, so that's the infinite limit that we derived last time. This is from the infinite the limit, product limit, Euler product limit. Okay. Infinite limit. We got this one. Last time we did like that. And now if you take the derivative of that or the inverse of that, because of the infinite product, if you use the product rule, that would be many terms that is very complicated. And we don't want to do that. We actually want to pick the log first and do the derivative, and because log of this infinite product becomes an infinite sum, that makes it easier. We can take derivative term by term. And now because of this z factor, we actually can use the property of the gamma function to simplify it a little bit, and we can divide the c into 3 and then write it as this is just 1 over gamma 1 z plus 1. This is just the property of the gamma function, right? But now, because of that, we actually want to take the log of that. This is the inverse of a function. Take the log of that, it's give you a negative sign. Log of. All right, so now you take the log of the right-hand side. So you have the first factor. Let's just give you gamma z. So take the log of exponential function, give you the argument. And now you can convert the infinite sum to infinite product to infinite sum. Sum of 1 and log of each term, right? And the log of each term has each term is a product, so there's 2 terms actually. So log of c over n, and then the log of exponential function, which give you the argument. Okay, so that's not too bad, right? So that's the this is the log of the gamma function c plus 1 with the argument c plus 1. You give it this form. This is actually pretty simple form, right? And now we take the derivative of that and define that as what we call what the textbook called the Digamma function. And the definition is in equation 36, basically is we defined it as psi using the same argument, c plus 1. So 1. And that is defined as just the derivative of this log. Okay, so that so basically this one accept the negative sign, so we can move the negative sign to the right hand side and take the derivative. What you get is the first one is give you a minus gamma. Move the negative sign, take the derivative. It's just give you a constant. Okay. And then the other one is see what put the negative sign in. And each derivative should be trivial. It says take the log of derivative of the log, just give you the derivative of 1 over this, and then the derivative of that give you 1 over n. And the second term is simply 1. But we can do a little simplification. So n, you can multiply that inside, become n by c, 1 over n by c, the first term. Simplify a little bit. If you want, you can write it as c plus n. That's one way to write it. I think this is yeah. This is like 13.38, except that we already set the n limit for n goes to infinity. And further simplify it is to write that as a product, that's the common denominator. This is n times z plus n, and then n minus z minus n, right? So n cancels minus z, so plus n plus z or z plus n, doesn't matter. Okay, so that is exactly 13.38. Okay, so we can get this definition of this infinite sum expression of this Digamma function. All right. It's okay, so this derivation is quite straightforward. And so and then the property is quite trivial, because this is just this all this product. I mean inverse power of this like inverse power of the c plus n factor, and then you sum of all of them. So that's give you some nice thing, because this infinite sum, we sum over inverse power of function, that is kind of common. So that give you at least formally you can write all this infinite sum in terms of this like this Digamma function, or later on if you keep taking derivative, you see that this one will give you more high and high power, like give you another derivative, which is c plus n squared, c plus n cubed, right? And so whenever you see this sum over inverse power of c plus n, something like that, then you can find at least if you want the analytic expression, you can try to express this into this Polygamma function, right? Yeah, you can write down this, keep doing derivative first, but then there's one more trick, that for special value of this function, basically you go back to this line, the first expression, not the second one, and then set the c equals to some special value. Say c is an integer. So the text will actually use m in here, and then use n in the other, because this is just dummy variable, so it doesn't matter. So change that to n, like your text. Right. and then you evaluate that C as at infinite n. Right. Yeah. Now you see that there's some cancellation because this is m obviously all integer or positive integer, right? If m plus n, you're subtracting, that's all the positive integer, but then you have delayed it a little bit. If n is positive, right? If n is negative, you get into trouble because somewhere along the line that would be singular, so you don't get n negative n here. So try a positive n, and you see that after a certain, I mean, this is like you cancel all the term up to m plus. So you have from Yap 1 and then up to the first one is n plus 1. So up to m up to n, those are all is left. For m is greater than 1 or greater than n, all those are cancelled because all the n plus 1, n plus 2, all those are cancelled. So that one. This is in the second term, so it's cross. We sum of n from 1 to n. Right. That is this expression. You can see that the cancellation, right? Because so this is exactly of the same form, just 1 over integer. This includes all integer, but this includes just the integer from n plus 1, start from n plus 1. So all the n plus 1 term and the larger integer in the denominator all are cancelled by second term. So you only keep the second term up to those terms that are not cancelled, which is 1 over n, and m equals to n, so you sum over up to n. Okay, okay, can you see that? And then there's a name for this summation. If it's infinite, this is called the harmonic series, which is divergent. We already said that. And now for this one, sum of up to a finite n term, this is called the harmonic number. That's called harmonic number. H of that is minus. Okay, and so that is just this is just a notation, but it's just in.
Is the left hand side gamma or is it phi?
What is gamma?
No, the left hand side is it gamma or phi?
Oh, yes. Yeah, right. Just copy it wrong. Okay, so that's a special value of this digamma function. Now once you have that, we can get rid of this. This is just coming from the derivation using the gamma function over this. And then keep the derivative, keep doing derivative. So one derivative is this one. One derivative give you this. Finally, this one. Well, either this one or that one. Depends on what your choice. And now define the high derivatives. Sin m. This is so the Polygamma function. This is just a notation. It's defined as easily m plus 1 derivative of log. Yeah. Okay. And compare with that, obviously, m is 0, you get the psi, right? M is 0 is this psi, right? And now that derivative is straightforward because it only operates on this term. Instead of using this one, we use this one. It's easier because keep doing derivative. If m is 1, you take a second derivative. So basically taking another derivative of that one will give you 1 over z plus m squared. Actually, minus 1 over z m squared. You get a minus sign. And then m equals to 2. We'll pick up a minus, another minus 2 factor, and z plus m cubed, and so on and so forth. So this is just keep doing that. And every time you get multiplied by the power, so you will get the factorial out. And because f is in the denominator, so every time you get a negative sign, so you have a negative minus 1 to the factor. In this case is this depends on what we want to write because there's a negative sign already, right? The next m equals to 1, we put a negative sign, will give you positive sign. So m equals 1 should give you a positive sign. So then m equals 2 will give you a negative sign. Right? And then it'll be a factorial number by keep doing the derivative of this power, negative power. And right. And so, like I said, if m is 1, then you take one derivative, you get the c plus m squared. Okay, c plus m. For this purpose, interchange m and m. Doesn't matter. Okay. So you get this d. M, this is m, this is n. C plus n, m plus 1. So m is 1, then you get the square out, right? And that is 1 factor is 1, and you get a positive sign. You get rid of the gamma because when you take the derivative, this is a constant. Okay, so that's so far so good, and you can check whether so this only applies up to for m greater than 1. Right? Because m is 0, it's like that, but for the 0 power, you get extra gamma. That is not included in this formula. So this formula only apply for m greater than 1. Greater or equals to 1. Is that okay? So, so that's the formula. Is that okay? It's straightforward. It's just derivative of power, inverse power. So that you just need to figure out all the coefficients. All right. Now again, there can be special value that you can just like you can put a integer or especially when for this one you put the 0 if you value at 0. So at 1, if c is 0, then this one is this ultimate formula. Sum of them 1 over n plus 1. And that is what we define as the Riemann zeta function. This part. We'll talk a little bit more about the Riemann zeta function. So all this polygamma function has some relationship with the Riemann zeta function. This is the definition, one of the definitions. zeta function, say this one equals the solution. Okay, and so that gives you some motivation why this Polygamma function is useful. At least for some special value, you recover zeta function. For special value, also this is integer. Right? This is m is the integer because you take the integer, the derivative, you don't take partial fraction of the derivative, although that can be defined, but then don't do that here. So this m is integer. Okay, so you get the integer value of zeta function this way. Okay, so that's one application, one special value.